Hey guys, Mr. Bowman here. So a bit of a different setup today. I've got Paint on the left and a bit of software called Desmos down the bottom. So if you do want to try it, please do. So Desmos, and today's learning objective is in black. We are learning to draw and identify equations of given, and then I've got a bracket, special lines. So what I do want to do is I do want to explain what this term means, and then on the right hand side we're going to get into drawing and going through some examples of these. So special lines. So what I'm going to say is I'm going to say our normal lines, and I'm going to put that in quote marks as well. That is always when it has the form y equals mx plus c. And we've mainly dealt with this type of line. And some examples, I'm just making them up on the spot. 2x minus 1, say negative 3 over 2x plus 4. All of those are examples of normal lines, and that's because they both have gradients and they both have constants, or that c value. So those are normal lines, but not all of the time they are going to look like those. Sometimes there are special lines, and that are equations, and these are just some examples. For example, when it's y equals 2. So we can see here that mx part has actually disappeared. Where's that gone? And then another example, what about x equals negative 1? And well, here what we've got is there's no m, there's no y, and that c has disappeared. Oh no, sorry, apologies, that c is there. That's the negative 1. So where are they gone? And the final example, y is equal to, let's say, 3x. Well, where's that c gone? So that c has disappeared somewhere. So what we're doing is we're just extending our maths. How does this y equals mx plus c rules work when you're missing certain components of that formula? Okay, and what I'm going to do is I'm quickly going to switch over to the Desmos side of our equation, of our computer, and we're going to get into some questions. Okay, so what I'm going to do is I'm actually going to put in that first example that we got up there, of the normal lines. So that's what our normal line looks like. And we're just going to leave that there as a point of reference. And what I'm going to do, y equals 2. Well, what that means is it doesn't matter what value of x is, every y value will be 2. So for me, what I'm going to do, I'm going to be looking at the y-axis at 2. And it is going to be a horizontal line because every single point y equals 2. So it doesn't matter what x is. And let's just check y equals 2, and we can see that. So we can see a horizontal line, and we can go back to the y-axis to figure out that that's y equals 2. Just an example, if I was to write y equals negative 3, I would anticipate a horizontal line going through negative 3 on the y-axis. So let's look if that works. Negative 3, perfect. We can see a green line pop up there. And just one more example, if I had y equals 5, I would expect through the y-axis a horizontal line to go through 5. There you go. So whenever you see a perfectly horizontal line, you know that's going to be an example of a special line. And all you need to do is you need to go back to the axes. So here we got 5, and that's on the y-axis. So that makes it y equals 5. So this one here, go back to the axis, that's 2, and that's touching the y-axis. So that's y equals 2. And then negative 3, so y equals negative 3. So that's an example of what we call a special line. Let's have a look at another one. So let's try to make it going the other way. So instead of being a horizontal line, let's make it a vertical line, a line going straight up and down. So let's try y equals negative 2. And we can see that black lines popped up. So it's a perfectly straight line. It's not on an angle. It's perfectly vertical. And if we go back to the x-axis, we've got negative 2. And that's where the equation comes from. So we've got x being the x-axis and negative 2 being the intercept on the x-axis. So what that means is if I'm trying to draw a line at y equals 1 here, sorry, x equals 1, Because it's on the x-axis, I'll need to be x equals something, and because it's at 1, I'll need it to be 1. So let's have a look. X equals 1, perfect, and that's drawn a line in our spot. And then final one, let's have a look at this 4. Because again, we're looking at the x-axis, so it's going to be x equals, and that's 4, so we're going to go x equals 4. There we go. And we've got 3 more examples of special lines, but they are all the x equals examples. And we can see if it's a perfectly horizontal line or if it's a perfectly vertical line, it's simply going to be x equals or y equals. And what you do is trace the line back to the axes, either the x or the y axes, and whatever axes it touch, that's the letter, the x or the y, and whatever number it intercepts at, that's what it will be equal to. Okay, so hopefully you understand the x equals constant and y equals constant lines. So what I'm going to do is I'm going to clear these and we're going to go through our final examples, and I'm just going to write down y equals 3x. That was the example we used before. And we can see these examples, they are on a line. And what that means is there is a value in front of x. So that means there is a bit of a gradient to these lines. And what makes it different is if it was plus 1, it would go through 1. So what makes these lines special is the absence of a constant is actually plus 0. So what that means is it's a special line because that line goes to the point of origin. So let's try some other examples. Let's try to make it less steep. So we're going to reduce that gradient. So let's say y equals 2x. There you go. We can see the steepness has gone down, or that gradient has decreased. But again, it's still special because it's going through the x-intercept, or the origin. And let's try y equals x. So at every point, 1 is equal to 1, 2 is equal to 2, 3 is equal to 3. So this one's special. Again, there's no constant, there's no plus or minus at the end. It's going through the origin at point 0, 0. So I've only used positive examples. Let's have a look at negative 2x. And again, the same thing. The plus 0 means it's going through the origin. And the gradient is negative 2, so it's going downward. And if you asked to come up with the equation of this formula, well, the y-intercept, well, that would be 0. So that means that plus c would be 0. And you would calculate the gradient using your normal rise over run methods. So we'll have a look here. Let's start at this point here. So that's 6. And we're going to go down to this point here. So it rises. It's actually going down negative 2 and across 1. So our rise over run is negative 2 over 1, which can be simplified to negative 2. And that's where we get our negative 2 and our negative 2x from. Okay, guys, hopefully you found this video on special lines useful. Just a recap, our special lines, so our normal lines are y equals mx plus c, where they have a gradient and they've been increased up or down. Our horizontal lines are y equals 3. Our vertical lines, where x equals, we'll call that negative 1. And our other form of special lines, ones that have a gradient but go through the origin, we'll call y equals x. So we've gone through 3 examples or 3 variations of our y equals mx plus c formula. Hopefully you found this video useful. Now let's get into today's questions. And if you're still listening, do comment in the YouTube comments below. Today's code word, we'll see how many people get it. But let's just say Desmos. All right, see you guys.